All right, so in this lecture, we're going to look at a new functional group. This is called the enolate. So this is going to be an introduction to enolates and enolate chemistry. Okay, so this is pronounced again, there's that en that we as chemists all pronounce as en, even though it is missing an e. Enolate. Okay, so enolate chemistry, these are alkoxides. They look like enols, but they're alkoxides where we have a double bond up to an oxygen with a negative charge. Okay, so you might be like, enols, don't they exist in tautomerization with a tautomeric form that is the keto? Sorry, goodness. Yeah, and that whole thing applies, except we're going to be looking at resonance structures instead of tautomeric structures. Okay, and this might be a little bit more straightforward than the tautomerization mechanism. So let's take an enolate. So I've got an enolate here. What I want to do is consider an alternative resonance structure and ask the question, which of these two species is a better contributing resonance structure? So on the left one, we have the oxygen with a negative charge. On the right one, we have the carbon with a negative charge. Now, between those two, we're forced to have charge separation. We can't neutralize the charge. Everything has an octet in both cases. We haven't broken any octet rules, either shorting the things 8 electrons or having more than 8 electrons. So they're both good on that account. But it's the left one that's better because the oxygen has a negative charge. But for the most part, it's this right one that describes the molecule's chemical properties and reactivity. Namely, what we're getting at is that the structure on the right has a negative charge at this position next door to the oxygen atom. And while that's not as good as a resonance structure, for the most part, we see reactions as though this compound has a negative charge at this position. Namely, what we're going to spend a lot of time doing for the most part when we're talking about these things, we're going to have this negative charge engage some electrophile, which I show as El+. And then we're going to put that electrophile at the position that once had that negative charge on carbon, but we don't often see a reaction at oxygen. We have to use actually some pretty specialized reagents that are what we call oxophilic. Okay, so that's going to be the focus of the lectures going forward. Now, the first thing I want to mention is we're going to have to start by figuring out how to generate this reactive intermediate. So these are enolates, generating enolates. Okay. For the most part, you can't just put these in a bottle. And buy these. Okay, rather you need to generate them. Okay, so they need to be generated. And what we do is we make them just like we make alkoxides. Okay, so we just kind of deprotonate them. It's not a big deal. We just add a base and we deprotonate them, and then we have these two resonance structures. So it's not overly complicated. What we have to recognize, though, is that we just have to make these before we use them. We're always going to start with the carbonyl, and then we add a base to it, and we get out our enolate, or in some cases, multiple enolates. And we'll look at that in just a second. Okay, so we make them just like alkoxides where we add some base. It's just the weird thing is we're going to consider this CH hydrogen as the thing that reacts with our base. Why is a CH hydrogen going to react with a base? That doesn't make sense. Hydrogen and carbon have very similar electronegativities, and they make strong bonds. Why would we want to deprotonate there? Wouldn't it make sense to tautomerize to an enol and then deprotonate the O? Yeah, but the equilibrium isn't favored, and it turns out this carbon atom is actually willing to donate its hydrogen to a base. Because what we do is we take that hydrogen, we push the negative charge, the base takes the hydrogen, pushing the electrons onto this carbon atom next door to the carbonyl position. And that's going to give our enolate structure. But we just went over that our enolate structure is actually stabilized by two prominent resonance structures. The one in this case all the way to the right, I guess it's the same as the one I started with, but that one all the way to the right is the best contributing resonance structure. But it's important to note that this negative charge is stabilized by resonance. So we have resonance stabilization of the negative charge, which means we have a stronger acid, right? Even though the CH is inherently not that acidic, anytime we can stabilize the conjugate base of something, we make itself a stronger acid. So that's what's happening here. This particular hydrogen, the one right next door to that carbon, is more acidic because the conjugate base, the resulting negative charge, is stabilized by resonance. Okay, so, and I should capture that. So because the negative charge in the conjugate base is stabilized by resonance, carbonyls are, I'm gonna add my word somewhat, whatever, word. They're not like as strong of an acid as HCl, but they're more acidic than your typical CH. More so than other CHs. Somewhat. And what are they somewhat? They're somewhat acidic. Sorry to not finish that thought. More so than other CH bonds anyway. Okay, so that's the point. Now, it's actually helpful to break down some positions related or relative to this position on carbonyls. So I'm going to talk about now, it's kind of a funny term, funny use of the word anatomy, but I think it works. We're going to talk about the anatomy of a carbonyl. So let's just look at a typical carbonyl, and I'm going to pick on an aldehyde here. I'm going to make this nice big structure. Okay, so I'm drawing a zigzag. Looks like 1 is the carbonyl, 2, 3, 4, 5, 6 carbons away from the initial carbonyl. So this would be hexane minus the E, add an Al at the end of it. Okay, so let's highlight this position next door to the carbonyl carbon. Okay, so I want to highlight the position next door, in this case to the right. This position has 2 hydrogens, and as we just said, these hydrogens are acidic. Now, it turns out I've chosen aldehyde for the reason that if we look at the aldehyde CH, the aldehyde CH is not acidic. If you try to deprotonate that, you put a negative charge right on the carbonyl carbon as opposed to next to it. We can't stabilize that one by resonance, only the one over to the right. Okay, so what we do to separate these two is we give them labels. This one all the way to the left that's characteristic only of aldehydes, I call the aldehyde, and you could qualify it as CH hydrogen. So you could call it the CH hydrogen or just the aldehyde hydrogen, telling you that this is that hydrogen that's not reactive to a base. We can't deprotonate it. We can oxidize it, do some funny stuff that way, but let's not worry about that now. Let's just worry about what happens when we add a base. Rather, it's those hydrogens next door. These are called alpha hydrogens, and I show my Greek letter for alpha. Alpha implying Greek letter for A. Now, those are my alpha hydrogens, which means up here, this is my alpha carbon. So we start with the carbonyl carbon, and then the first carbon next door, that gets the letter A in the Greek alphabet. That's the alpha carbon, and attached to it are the alpha hydrogens. So let's make note of this right away. Alpha hydrogens are important. They are particularly important for enolate chemistry, but they are important because they are acidic. Okay, so you want to know what alpha hydrogens are. You want to know what the alpha position is. That's one thing I need you to take with you when you're done with this class if you want to continue thinking about molecules, especially those in biology, is know what an alpha position is. We have a carbonyl. Next door is the alpha position. In fact, that's where the alpha comes from in alpha amino acids. We put the nitrogen alpha to the carboxylic acid, which is also itself a carbonyl. Okay, we can actually continue down. We have hydrogens here, 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 here. In this particular example, the only ones that are super important are the alpha hydrogens. And we could keep going, so I'm just going to draw 2 of the 3 at the end. So we have the alpha carbon. Next to the alpha carbon is the beta carbon. We'll talk about beta carbons a lot in upcoming lectures, but for now, they're not super important. It's the alpha carbons and those alpha hydrogens that are important. So we have our beta carbon. I'm not going to label the hydrogens as beta hydrogens, but you could. They're just not that they're not that fun compared to the alpha hydrogens. So we go alpha, beta, gamma carbon. D is delta carbon. And then we have E, which is the epsilon carbon. We have like a curly E. So we go alpha, beta, gamma, delta, epsilon if we need to. And at the end of the chain, maybe there's like an omega or something. But it's the alpha position, and then in a few lectures, the beta position that are most important. The alpha position is important to us right now because it has with it alpha hydrogens. Those are acidic. What I want you to be able to do now is recognize an alpha position in a carbonyl and separate it or distinguish it from an aldehyde position or an aldehyde hydrogen. The aldehyde hydrogen does not react with base. It's the alpha hydrogen that reacts with base. So what we need to be able to do is look at carbonyls and draw. We need to, let's do it this way. We need to react carbonyls with a base and draw the resulting enolates. Okay, let's look at some examples of this. So I'm going to start with an aldehyde right away. I'm going to add some base to it, and I want to draw my enolate over here. What I first want to count is that there's only one H atom that's at the alpha carbon. So there's only one alpha hydrogen, and it's that one that's located at the only alpha carbon. It turns out that if you're keeping track of betas and that sort of thing, we have 2 beta positions, but it's this one alpha hydrogen that's attached to the alpha carbon. So when we add base to this, we are going to form the resulting enolate, which I show as a carbon with a negative charge. Okay, so this is okay for me. This is all you need to provide for me if I say draw the enolates. But be aware, now I'm not saying worry. I'm not saying the words worry. Don't worry about this, but just be aware that CC stereoisomers are present. What do I mean by that? Well, let's draw that enolate that we drew correctly, that was good enough for me. Let's draw that enolate because you didn't deprotonate the alpha hydrogen. I'm going to consider a resonance structure of that. The negative charge comes down. And if I do, if you notice, I have the opportunity for E and Z alkenes. That's a Z. Looks kind of like a second E. E and Z. Now in this case, we are Z-zame-zide. We're Z because we have priority 1, priority 1, priority 2, priority 2, Z same side Z. So we have a Z enolate here versus the E enolate, where in this case, the right sides have flipped. You could flip either side, just do it once. Sorry. 2, 3. One more. Okay. So now this would be E. So E and Z enolates can exist. And you might ask, aren't they just resonance structures of each other? No, they're actually like stereoisomers of each other, because we've rotated over a bond that probably doesn't have that much free rotation character because there's such a strong resonance contributor where it's a double bond. But drawing a negative charge at that position would have been just fine. Okay. So we need to be aware that the aldehyde hydrogen does not react to the base. We also need to that's something we need to know. We need to worry about. We need to not mess that up, that we're not deprotonating the aldehyde hydrogen. Now, what we don't need to worry about, but just be aware of, is that you can have E and Z enolates. Okay, so let's also recognize, and this is something I want us to worry about, that multiple enolates can form if multiple alpha carbons are present. Okay, so what do I mean by that? Well, let's say we've got this molecule. This molecule is symmetric. That is, if I look at the alpha position on either side and I grab one of the 3 hydrogens on either side, if I did my little NMR trick where I'd say, are they the same? You'd be like, yeah, both of those would be like considered an HA. And so if you treat that with base, if you draw an enolate at either position, it's the same. These two structures are equivalent. They can roll over in 3-dimensional space, and it's the same outcome. They behave the same. But if we flip, if we destroy the symmetry, then all of a sudden we've got an HA and an HB. And if we treat with base, then we get 2 enolates that are not equivalent. So remember, base is going to replace the alpha hydrogen with a negative charge. In this case, we get 2 different intermediates. Two enolate intermediates that can form. They're both enolates. One you could call A and B. That's because we have 2 different alpha carbon atoms. Okay, so we have one enolate due to symmetry. Then we have no symmetry. So we have 2 enolates that can be formed. So you're just kind of looking at that alpha position, that carbon right next to the carbonyl carbon. See if it has some alpha hydrogens, if it is present. Now see if those are the same on either side. So as you would expect, if you've got just one carbonyl, you have a maximum of 2 possible enolates that you can form. There's a few little tricks in here where if you've got a benzene ring on one side, all of a sudden you've got an alpha carbon with 0 alpha hydrogen atoms. And so if you treat this structure with base, you then remove here and here, and you get one outcome, which is this structure here. So only one enolate can form. Okay, what I want to do now is just briefly talk about the reactivity of these things and how they behave when certain electrophiles are present. I kind of alluded to this before, that we're going to engage these things with electrophiles, and it's that resonance structure showing the negative charge at carbon. It seems to be the most helpful for understanding how these things react. So, reactions of enolates. For the most part, mostly we see electrophile additions to the alpha carbon, which is negative. Okay, so we treat our carbonyl with a base. That base then removes the alpha hydrogen. You can make that base negatively charged. It removes an alpha hydrogen. And then even though we have a resonance structure that's better where we put the negative charge on oxygen, we typically see the molecule behaving more like the resonance structure on the left, showing the addition of an electrophile to the alpha position. And we get alpha substitution. Okay, so how do we get reaction at oxygen? I'm going to mention that now because it's kind of important that we touch on that and then move away from it. So an approach to how to get reaction at oxygen is to add an what we call an oxophilic, that is an oxygen-loving or has a high affinity for oxygen atoms, an oxophilic electrophile. And really the only one I want us to be somewhat aware of is if you have a silicon with a halogen atom attached to it. So I'm going to put 3 CH3s, 3 methyl groups on the silicon atom, and we're going to let that react with our enolate structure. And it's here that the oxygen is going to engage silicon and push off the chlorine atom to give the oxygen substituted species. Because the silicon-oxygen bond is strong. Okay, so the takeaway there is for the most part, we're going to see reactions at carbon, and that's what we're going to look at. We're going to kind of go through some typical bases, then we're going to look at some electrophiles like haloalkanes and that sort of thing to do SN2-like reactions. Then we'll get into the real meat, which is the aldol reaction and the aldol condensation. So until then, I'll see you next time.